In this example, we're going to determine the empirical formula of a compound that does contain oxygen. In this example, we are combusting 18.8 grams of glucose. Now, we know that glucose has carbon, hydrogen, and oxygen in it. So we know that we're going to have to account for the difference between the mass of carbon and hydrogen and the original mass of the sample. So as before, we take our mass of carbon dioxide and water and we determine the mass of carbon and hydrogen in each one of them. We also want to determine the number of moles along the way and save that information. So as before, we take the mass of carbon dioxide divided by the molar mass and then multiply it times the ratio of carbon to carbon dioxide in the formula. Once we have our moles of carbon, we are going to multiply that times the atomic mass of carbon to find out the number of grams of carbon in our sample. Always check your dimensional analysis along the way. Make sure you're doing this right. Now we perform the exact same operation with water. Divide the mass of water by the molar mass of water, then multiply it times the ratio of hydrogen to water molecule. Save the moles of hydrogen. Check your dimensional analysis. Convert moles of hydrogen to mass of hydrogen by multiplying it times the atomic mass. And finally, we take the mass of carbon and hydrogen that we calculated, add them up, and we subtract that mass from the mass of our original sample. Notice this time that the mass of carbon and hydrogen is much less than the mass of the entire sample, which means that the rest of the mass must be oxygen. Once we know the mass of oxygen, we are going to convert that to the number of moles of oxygen by dividing it by the atomic mass of oxygen. So now, if we've saved our old information, we have the number of moles of carbon, moles of hydrogen, and moles of oxygen. Now we're going to determine the lowest whole number ratio of these three components the exact same way we've done before. Now in this case, we can probably tell that our carbon and our oxygen are in a 1-to-1 ratio to each other. But we're going to stick to the usual example, and we're going to divide all of these by the number of moles of carbon. That's the lowest mole quantity we calculated so far. This means that for every 1 mole of carbon, we have 1.9996 moles of hydrogen, or 2 moles of hydrogen, and 1.0033 moles of oxygen, which is essentially 1 mole of oxygen. Which means that the empirical formula is CH2O. And that's as far as we need to go, unless we've been given a little bit more information about glucose. If we measure the molar mass of glucose to be 180 grams per mole, we can compare this to the empirical mass that we calculated. So that is 1 carbon, 2 hydrogens, and 1 oxygen. That gives us an empirical mass of about 30. That's much less than our molecular mass. So we're going to divide our molecular mass by our empirical mass to find out by what factor we are off by, which is 5.995. And that is essentially 6. Again, as long as you've done everything correct, this should come out to be an integer when it comes to the factor between the molecular and empirical formula. So we're going to take each one of the subscripts in CH2O and multiply them all by 6. That's going to give us C6H12O6. And you can look this up on the internet and determine that yes, that is the molecular formula for glucose.